Hi everybody. In this video we are going to look at the solutions to the honors magnetism homework problems 11 through 14. You may be wondering why there's only 14 or 4 problems in this homework set and not the usual 5. I'm blaming budget cuts. All right, let's take a look at number 11. We have a 0.58 meter long wire carrying a current of 30 amps. It is oriented perpendicularly to a uniform magnetic field. The wire experiences a force of 0.05 newtons. They want to know what is the strength of the magnetic field. So our givens in this problem are the length of the wire at 0.58 meters, the current at 30 amps, the force at 0.050 newtons, and we are looking for the magnetic field. With the length of the wire, the current, and the force, looking for the magnetic field, I'm going to want to use F equals ILB. I'm solving for the magnetic field, so that is going to give me B is equal to F divided by I times L. Plug in my known values of 0.050 newtons for the force, 30 amps for the current, and 0.58 meters for the length, and that will give me a magnetic field of 2.9 times 10 to the minus third Tesla. Problem number 12. An electron experiences a maximum outward or positive Z force of 2.5 times 10 to the minus 12th newtons when it is moving at a speed of 2.1 times 10 to the 6th meters per second toward the north. What is the direction and magnitude of the magnetic field? Let's look at the magnitude of the magnetic field first, and then we'll take a look at the direction. So in this problem, we are given the force, which is 2.5 times 10 to the minus 12th newtons. We are given the velocity of the electron, 2.1 times 10 to the 6th meters per second. And because it is an electron, I know the charge of an electron is 1.6 times 10 to the minus 19th coulombs. And we are looking for the magnitude of the magnetic field. So to find the magnetic field, I'm going to want to use F equals QVB. Solving that for the magnetic field is going to give me B equals F over Q times V. So I plug in my known values. One thing I want you to know is that even though the charge of an electron is negative 1.6 times 10 to the minus 19th coulombs, I'm just going to use the absolute value of that when I plug it into the formula, because remember, the math only gives us the magnitude, not the direction. We get our direction by using the right-hand rule. Typically, the negative, positive, and negative sign in an equation will give us a direction of whatever vector we're solving for. But in this case, we're using the right-hand rules for our directions, so I can ignore that negative sign. When I do out the math, I am going to get a magnetic field of 7.4 Tesla, and it is going to be to the east. And let's take a look and see why that is. We know that the force is in the positive Z direction. So I know that that is going to be my force. I know that my velocity is in the upper direction or toward the north. So if I use my right hand, one other thing I do want to note with this is that we typically use the right hand rule. So we use our right hand. In all of these videos, I've been using my left hand because it's a mirror image, but because we are dealing with an electron, we're going to need to use the opposite hand that we normally would. Because remember, the right hand rules always apply to a moving positive charge. And if for a negative charge, we have to use our left hand. So because we are dealing with a negatively charged electron, we would use the opposite hand of whatever we would normally do. For you guys, that would mean using your left hand, but because I'm doing the opposite of the opposite here, I'm going to have to use my right hand for this. So my fingers always denote the direction of the velocity, and that is going to the north. My force, which is represented by my thumb, is going to be the direction of the force, and the force is in the positive Z direction or out of the screen. So my thumb should be pointing toward me. My fingers for the velocity should be pointing upward, and my palm, which represents the magnetic field, is pointing in the positive x direction or to the right from your perspective. So that would mean that the magnetic field is oriented, and you could say either to the east in the positive x direction, to the right. All of those mean the same thing and would be perfectly legitimate answers. Problem 13. A thin 1.3 meter long copper wire has a mass of 0.09 kilograms and is levitated in a uniform magnetic field of 1.4 Tesla. The first part of this problem asks us to show on the diagram all of the forces being applied to the wire. The key word and the thing that we need to really pay attention to here is this word levitated. The wire is being levitated, which means that it is floating stationary above the ground. So if I want to think about the forces that are acting on this, of course we have the force of gravity acting on the wire, and that force is oriented straight downward toward the earth. But in order to get it to levitate or to float motionless above the ground, we need another force counteracting that force of gravity. And that second force that is going to be counteracting gravity is going to be the force generated by the magnetic field on the wire. And that's going to be pointing straight up, and that is going to oppose the force of gravity or balance out the force of gravity so that the forces are in equilibrium and the wire will levitate. Part B of problem 13 asks, what is the net force on the wire if it stays at the same altitude? So I know that the net force is equal to the mass times acceleration. And remember, this Greek letter sigma means that that is the net force or the sum of all the forces acting on the wire. And if I look back at my free body diagram from the previous slide, I know that the two forces acting on the wire are the force of the magnetic field acting upward and the force of gravity, which is equal to the mass times gravitational acceleration acting in the downward or negative direction. So I can say that the magnetic force minus the force of gravity is equal to the mass times the acceleration, which is equal to 0. And I could also say that the magnetic force is equal to the force of gravity. And because both of those equal 0, because my acceleration is 0, because it is not moving up or down, I can say that the net force acting on the wire is equal to 0. Part C asks, what is the direction of the magnetic field? So here we're going to use our right-hand rule. And remember, in these demonstrations, I'm using my left hand because the camera acts as a mirror, so my left hand looks like your right hand, but you always need to use your right hand because these are, in fact, the right hand rules. So remember, when we are using our right hand rules, our fingers are always in the direction of the current. My thumb is going to point in the direction of the force, and my palm points in the direction of the magnetic field. So if I had an arrow shooting straight out of my palm, that would point in the direction of the magnetic field. So in this problem, we have the current in the negative z direction. That's what this x here signifies, that that is in the negative z direction. So I want to point my fingers toward the screen or into the page. My thumb is in the direction of the force, which is upward. And remember, it's the magnetic force that we're talking about here. So my thumb points in the direction of the magnetic force, and my palm is in the direction of the magnetic field. And my palm is shooting to your left, or we can say toward the east, or I'm sorry, towards the west, or in the negative x direction. So the magnetic field is pointing to the west or negative x direction. The last part of problem 13 asks, what is the magnitude of the current flowing through the wire? Typically, when we're using F equals ILB, we need to know what the magnitude of the force is. We're not given that in this problem, but we do know that the magnitude of the magnetic force is going to be equal to the force of gravity because the wire is levitating in the air. And I know that the force of gravity is equal to mass times gravitational acceleration, so I can replace mg for the force of the magnetic field in my formula F equals ILB. And when I do that, I'm going to get ILB is equal to mg. Solving that for the current, I'm going to get I is going to equal to mg divided by B times L. Plug my known values into the equation, and that will give me a current of 0.48 amps. Problem number 14. A proton is traveling horizontally at a constant speed of 7.40 times 10 to the 6 meters per second when it enters a uniform magnetic field of 0.460 Tesla. And they give us a diagram which shows us that the magnetic field is in the negative z direction because of those x's. It tells me that it is pointing into the screen. I am given the direction of the velocity in the positive x direction, or to the east. So when I use my right hand rule, I have to turn myself a little bit here. I know, again, using my left hand, that my palm wants to point toward the screen. And my fingers, which represent the velocity, want to be pointed in the positive x direction or to the right. My thumb here will give me the direction of the force, and my thumb is pointing upward. So my force generated by the magnetic field is going to be in the positive y direction, or upward. Part B of problem 14 asks us to show the approximate path of the proton. The important thing to notice here is that my force vector and my velocity vector are at right angles to one another. And whenever we have a force vector that is perpendicular to the direction of the motion, or perpendicular to the velocity, that is a centripetal force. And centripetal forces cause things to move in a circular path. So this force, while the proton is moving in the positive x direction, if my force is to the north, it's going to want to cause the proton to move in a counterclockwise direction because it is a centripetal force. Part C of problem 14 asks us to calculate the magnitude of the magnetic force on the proton. So if I look back and see what the givens are in this problem, I know because I have a proton that my charge is going to be 1.6 times 10 to the minus 19th coulombs. I know that my velocity is 7.40 times 10 to the 6th meters per second, and the magnetic field has a magnitude of 0.460 Tesla. If I use F equals QVB and insert those values into the equation, I am going to get a force of the magnetic field of 5.44 times 10 to the minus 13th newtons. Part D asks us to find the acceleration of the proton. So if I'm looking for the acceleration, I want to use Newton's second law, F equals ma, F equals mass times acceleration. Solving that for acceleration, I want to divide the force by the mass. So the force acting on the proton, which we found in part C, was 5.44 times 10 to the minus 13th newtons. Divide that by the mass of a proton, 1.67 times 10 to the minus 27th kilograms. And I'm going to get an acceleration of 3.26 times 10 to the 14th meters per second squared. The last part of problem 14 asks us to calculate the radius of the path that the proton follows in the magnetic field. Now remember, this is a centripetal acceleration that the proton is undergoing because it is moving in a circular path. So I know from from when we studied circular motion way back before the holidays that the centripetal acceleration is equal to the square of the velocity divided by the radius. Yes, I know that was a while ago, but remember, this stuff never goes away. As long as I'm around, it's not going to go away. So until I have a burrito or two, you guys are going to be working with centripetal forces and centripetal accelerations. So to solve this formula for the radius, I know the radius is going to equal the square of the velocity divided by the acceleration. So I plug my known values into the equation, and I'm going to get a radius of 0.168 meters.